Okay, we're starting. Okay, so last time we started talking about dimensions and involved a bunch of things. But just to remind ourselves, we spoke about linear independence. And what does that mean? Say a set of vectors are linearly independent. What does that mean? Yeah?
Cannot be, any vector cannot be expressed as other linear combination.
Sure. Give me something we can check. When is that true? When can I know I'm in a situation where no vector can be expressed as a linear combination of the other vectors?
When they're linearly dependent.
When the only coefficient that you made.
To say a set of vectors v1 through vn are linearly independent, what am I saying? How can I check that?
Well, if you put them into these AV1 plus AV2 form, all the coefficient has to be 0 in order for them to equal 0. The 0 vector.
As only and no other solution, only the trivial solution for Ci. Right? I mean, all the C's have to be 0 in order for that equation to have a solution. What about saying that V1 through Vn span some vector space V? What is that saying? Yeah?
Any member of V can be expressed as a linear combination of the vectors that constitute a span.
Right, so any vector in V can be expressed as a linear combination. V1, V2, and so any V, I can write it as a linear combination of those guys. What's a basis? Yeah?
The vectors in V that are linearly independent and they're both linearly independent and they span V.
So it's a set S that is 1, linearly independent, and 2, S spans V. Dimension. How do I define the dimension of a vector space? Yeah?
Dimension of V is an integer that describes the number of vectors in the span, in the basis of V.
Yeah, dimensions of V is pretty much the number of vectors in a basis for V, right? And of course, we're talking about finite dimensional with finite. Otherwise, we define the dimension of V to be an infinite dimensional vector space. What's the importance of finding a basis? Why would we care about finding a basis for a vector space? Yeah. You can find coordinates, you can talk about location. Essentially, it helps us set up a coordinate system. And of course, changing coordinate systems. So you can talk about some sort of location using bases in terms of the C's that are in front, in terms of an ordered basis, and we can actually use those guys to, we can look at our world in terms of these guys. So it's just like it's convenient sometimes to think of things in R2 as something times the I vector plus something times the J vector. And we've seen throughout Calc 3 that doing this, thinking of things this way, it's useful. It helps us to locate things. We can come with the equations of curves that we care about using these things. So the basis really gives us a description for the space that we care about, and it's a way to locate things and set up coordinate systems and hence define things, objects of interest in our system. So it's a very important thing to be able to find a basis for a vector space. It helps us do a lot of things. It turns out that a basis, if something is a vector space, it is guaranteed to have a basis. We're not going to prove that. To prove that, you actually need some high-level set theory, which we're not going to get anywhere close to touching that. But we can also build one up if we already have some facts. I don't remember what did I tell you. Yeah, I'm pretty sure I told you that. You know, we did the dimensions of that, and we found that. Some useful theorems, besides the one we did last time. I'll tell you these and move on because they're important for on a theoretical basis, but we're not really going to use them in this class. We're not really going to build things up. Usually if we're searching for a basis, there'll be a systematic way for us to find it. It's usually going to be some sort of row reduction. But these are useful like in general. When you're dealing really with a very strange vector space, these can kind of help you. And it's also things that you should at least have heard of taking a linear algebra course. There's something called the plus-minus theorem. So this is basically saying that comes in two parts. It's talking about adding and subtracting vectors. If S is linearly independent set in V and V is not in the span of S, then if you take the set S union, if you add that vector, so the set plus that vector is still linearly independent. So adding a vector to a set that's already linearly independent, that's not in the span, the set will stay linearly independent. So this is kind of telling you that if you want to come up with a basis for a vector space, you already have a bunch of vectors that you know are all linearly independent, but they don't span the set. The idea is you can keep adding vectors until you get to a basis, right? Because finding a basis is important. All you have to do is make sure that the guys you keep throwing in maintain the linear independence of the set.
So could you have a bunch of zero vectors?
No, because we have a theorem that says if zero vector is a member of a set, it's not a basis because they will be linearly dependent necessarily. because you can always multiply the 0 vector by a non-zero constant and everyone else by 0. And you can solve this guy. If this vector is 0, then I don't have only the trivial solution. I can literally put anyone here and then 0 is everywhere else, and that's the solution. Right? So 0 cannot be in any independent set. And then there's the minus part. So if S has a dependent vector V, and we minus this vector, remove V from S, then we don't change the span. Then the span of this set, S minus that vector V, is actually the span of the original. In other words, what the plus-minus theorem tells us is that we cannot always, starting from these two starting points, we can always create, ultimately build up to a basis or cut down to a basis. So if I have something that spans a set, but it doesn't have linearly independence, I can literally just keep throwing away vectors that make it dependent. Eventually, I would keep the same span, but then it would eventually get to a point of independence. And if I have independence, but I don't have span, I can keep throwing vectors in to enlarge the span, but keep the independence. So basically, this means always build up or cut down a set of vectors to get a basis. It also means that every spanning set either is a basis already or contains a basis. As a subset. And this is, again, we're never really going to use this theorem. This is really when you really have no idea about the space you're studying. You have reason to believe that it might be a vector space. So you just start with this random group of vectors in that space and kind of see, can I create all the other vectors from this set I have? No? Let's throw some other vector there. Now can I do it? No, and then eventually you get somewhere where you're like, okay, that's too much because now I lost linear independence. I can literally find the guys that are dependent and throw them away. And then eventually I can, through this process, create a basis for the set, which is going to be an important thing. And as we will find, we can change this basis. So let's say we ultimately create a basis for a space, but I don't really like the basis vectors that are there because they're not convenient for me. I can always change them to another set of basis vectors that are more convenient. And that's really in the next section that we're going to do that. And that's going to be more computation. We're actually going to do some computation over there. Here's another theorem that might come in handy, which hopefully it should be somewhat intuitive. It should be believable just by hearing it. If V is a finite dimensional vector space, and W is a subspace of V. Okay, now let's remind ourselves, what does it mean to be a subspace of a vector space? It's a subset that is closed under the addition defined on the space and the scalar multiplication defined on the space. Once you verify those two things for a subset, turns out that set is a basis, is a vector space on its own, and we call it a subspace. Okay, so 1, the dimension of W is also finite, meaning a subspace of a vector space can't have a larger dimension. 2, we also know that the dimension of W has to be less than or equal to the dimension of the original. And 3, the dimension of W is exactly equal to the dimension of V if and only if the W is actually equal to V. Right? So if you have a subset and you realize that its dimension is the same as the original set, it turns out that that subset is exactly the same as the original set. Which, by the way, that might not always be obvious. It might seem obvious me writing it down, but it might not always be obvious. Because you might have this set expressed in terms of different representatives and you're not sure. But once you can be sure once you calculate the dimensions.
What happens if dimension of W is greater than the dimension of V?
That would be impossible. That's by 2. It's always going to be less.
Because it's a subspace?
Because it's a subspace, right? So you can't have like a subspace of R3 being a 4th dimensional thing. So if you're a subspace of R3, you have to yourself be R3, or be some 2-dimensional set, or some 1-dimensional set, or some 0-dimensional set. So the subspaces of R3 is R3 itself, or planes that pass through the origin, which are the 2-dimensional objects, or lines that pass through the origin, which are the 1-dimensional objects, or literally the coordinate, the origin, which is a 0-dimensional object. Or the 0 vector is how you would think of that. Okay. So, let's actually do some. We've been doing a lot of theory these past couple of classes. Let's actually segue into some examples here. Some things that would be useful that I can like ask you on a test in terms of the computational stuff. We're going to move on to 4.6, change of bases. This is basically tackling the change of basis problem. That is, given a basis, how can we express vectors in terms of this new basis? That's the question. Let's actually sort of try to figure this out using an example, and then I'll actually tell you the formula for it, because there's actually a nice formula for it. So let's do an example here. We're in R2, so let B 1, so this is the IJ, the standard basis. B2 is going to be this guy, 1 minus 1, 1, 1, and B3 1 minus 1, comma 0, 2. So what do I want to do here? I think we actually did examples of these before. let's do this. How would we change v? And remember, this is just the coordinate vector in relation to b2 to v in terms of b3 is an example of the question I want to ask. Where, I didn't tell you what these guys are, where we're going to do a specific example. This guy is equal to minus 1, 3 in terms of B2. Okay, so this means what? If I say v with respect to the base, the coordinates of v with respect to the basis b2 is equal to minus 1, 3, what am I saying?
The solution to the matrix you form with B2, the solution to that matrix is negative 1, 3.
Yeah, but well, how would I express that? How would I say that? What is the vector that I'm talking about?
So C1. Yeah, C1 is negative 1. So it's negative 1 times 1 negative 1.
Times the first basis?
Yeah.
Plus
3 times the second. 1.
1, 1. Okay, so what is the actual vector that I'm talking about? In the standard basis. 2?
Yeah.
2, 4. So in the standard basis, by looking at this vector in R2, this is really the vector 2, 4 that I'm talking about. But when I write that vector 2, 4 in terms of this basis, that's the vector, okay? And this is how we get it. So now I'm asking you, how do you think we'd go about computing B3? Right, now the idea is, you want to kind of set this system up, right? C1 times,
1
what's B3?
1 negative
1 negative 1 plus C2 times
0,
0, 2. But here's the goal. I don't want to actually transfer to the standard basis and then come here. I want to actually, is there a way to go directly from here to here?
Yeah.
How do you think you could accomplish that?
I think if you augment the matrix with the solution set, negative 1, 3. If you make a matrix that's 1, 1, negative 1, 1, and then negative 1, 3 is the solutions. And then you turn that matrix into, like if you do the thing where we did the row operations to find the inverse,
Mm-hmm.
if you do that and make it 1, 0, negative 1, 2, then your solution set will be the solution set for this one.
I think I get what you're saying, and I think that's correct.
Okay.
We do want to streamline the process, though. So it turns out that, yes, but there's an easy way to construct that matrix you're talking about. The idea is, because these guys are bases, I can express any vectors in R2 in terms of these guys. So the nice way to do what you just described is to really, what if I could somehow change this to be in terms of some constant times the other bases, in terms of the other basis vectors, 1 minus 1 plus d times 0, 2. And I can at the same time change this guy to be e times 1 minus 1 plus f times 0, 2. And now you see if I just like expand the parentheses and regroup, I can eventually figure out the constants that would do it here, right? So it turns out that process it's going to be a lot more streamlined, especially if you're dealing with larger matrices, right? So what would that mean? How would I need to express this in terms of that?
It's negative 1 times 1 plus 0. 1 times the first matrix, 0 times the second.
But let's actually call these. So 1 and 2. To solve for, can you actually see this? I don't know. I hate these markers, they die so quickly. It's this one. Okay. To figure out 1, what would we do? We said this is what we were doing last week, right? We put the solutions here, and then I would try to find the guys that does that, right? Because I want to figure out some constant times this plus some constant times that equals this. And to figure out 2, I need to essentially do the same thing times the other basis vector. In other words, I'm trying to find a way to express the basis vectors in the first situation as the basis vectors of where I want to be, right? And it turns out I have to solve these two systems, right? But here's the thing. Doing a row operation here, doing a row operation there, remember the ultimate goal would be to get the identity and then you can read off the solutions. But notice that what I do here is going to be exactly the same thing as what I do there. And so we can kind of combine these two and do it all at once, is going to be the idea. Let's solve it for this to get that guy, but at the same time, let's solve it to get this guy. And just reduce one big matrix, and I could immediately change these guys, right? I could immediately read off the solutions for both. In other words, here's what I want you to get the picture as being. What we would do is we would set up, right? And this is going to help me figure out what matrix I need to multiply this guy by to automatically transform it to that basis, right? So do you notice what we actually put here and here is what went in the first section, which I can put in. I was going to put a different color, but the colors aren't working out for me. Here is the new basis that I want to change to. So I just put all the basis vectors from the vector space, the basis that I want to get to, right? So in B3, I want to end up in B3. I would put those basis vectors, line them all up here in columns. And what comes over here is the old basis. That I want to change from. And the idea, of course, is once I actually reduce that, find the reduced row echelon form, to find the solution, what would the left side be? The identity. Why? Because the vectors are linearly independent. They form the basis. And so here, I'm going to get some matrix, right? And this is the matrix that I'm going to actually take, and I can multiply this vector by 2 we're at 1, 3. Minus 1, 3. And that's in terms of B2, and that will give me the result in terms of B3 automatically. This guy here is called the transition matrix. And in this case, it's from B2 to B3. And there's a standard notation for this. They usually write a big P, and then the subscript would be, you put the vector space where you're coming from, B2, you put a little arrow, and you write B3. Yes?
I'm sorry, can you explain in the steps 1 and 2 how you set those up again?
Oh, well, the goal is I need to solve, this is because I need to find C times 1 minus 1 plus D times 0, 2. I need to find a way to express this guy in terms of those guys.
Right, and that makes sense, but I just don't understand.
And then this guy, I need to find a way to express this. As that guy. Right? So I want to write this basis vector in terms of those two basis vectors. And then I want to write this basis vectors as a linear combination of the other two basis vectors. But if I set up a linear system here,
Why are they the same? Why are they the same? Why are they the same vectors?
same vectors where?
In both equations, in both the CD part and the EF part, why are they, I don't understand why they're the same.
These are the basis vectors for B2. So I can express a vector in terms of a linear combination of those guys, and that's in the B2 world. I want to change from the B2 world to the B3 world, which means I don't want to express my vectors in terms of these guys. I want to express my vectors in terms of these guys. So my goal in the shortcut for doing that is, if I can express each of these individually in terms of those guys, then I'd be able to express the entire thing in terms of those guys. So one at a time, I focus on changing this guy to be written as a linear combination of the vectors in B3, and I change this guy to be written as a linear combination of the vectors in B3. Right? So they'll both have the same vectors here. Right? Now, when I write this as a system of equations and augment it, it's going to look like this. If I write this as a system and augment it, it's going to look like that. Right? And I'm skipping a few steps here, but we've actually done it in previous classes. If you just go through and sort of take it slowly, you'll see that that will come to be, right? But now I realize, well, this part of the thing is going to be exactly the same. The only difference is going to be the last column, the constant column. So I'm saying, since I'm going to do the same row operations to get to the identity anyway, might as well do both of them at once. Right? And then doing both of them at once makes it kind of lined up in this way, where I just put the basis vectors on the right of the space I want to change on the right side. The old basis vectors go over here, and the new basis vectors go over here, and I just reduce that all at once. Now reducing that is going to give me this. It's going to tell me how to change this and that simultaneously. And so I'll be able to take that matrix to be able to express this vector in terms of these guys right away, just by multiplying.
So the matrix on the left and the right is set up a new basis that I want to change to. So like that's.
Yeah, so these guys here were the B3s. Right, those guys were listed in my B3. And these guys here, you'll notice, are the vectors from B2. I put the basis vectors from B2 here, the basis vectors from B3 here. And that's me trying to figure out, how do I get from B2 in order to end up in B3? Ultimately, when I set up the system of equations, that's the kind of system I have to solve. And so what it is the old basis to transform to the new basis, I set up this system and solve it.
So there's some sort of linear transformation from B3 that's going to allow you.
Yes, there's a linear transformation from B2 to B3.
Or vice versa, I mean, you could call it a direction.
In fact, that's something I'm going to say later. There's always a vice versa. There'll always be a way to go back, and in fact, it's going to be the inverse matrix, which I know exists because they're linearly independent, so the determinant will be non-zero by the theorem that we had way back when.
Can we see an example problem now that we've set it up?
So we're going to do this example. I just kind of want to explain where that formula is going to come from. So I'm going to do this example by using this setup. I just kind of wanted you to see where that setup was coming from. So basically, the upshot of it is this: if I have one set of basis vectors, and I want to figure out how to express coordinates in another set of basis vectors, what I can do is line up the old basis vectors in order on the right side, line up the new basis vectors in order on the left side, reduce that entire system using row operations. The matrix I end up with here will be the matrix that tells me how to transition from one basis to another basis. And if I take that matrix and multiply any vector in terms of this basis, it will transform it into a vector expressed in terms of that basis. Right? So let's actually do that here. Okay, so we're going to apply this. So we're given a vector in terms of that basis. We need to find that vector in terms of B3. This means we're going to set up this system of equations, which I already set up over there. I'm going to find the reduced row echelon form of this, which I'm going to skip for the sake of time. It's the same reduced row echelon form we've always been finding. You'll always end up with the identity here, of course, because they're linearly independent. And in this case, on the right side,
0 and 1 on the bottom.
you ended up with that. Right. Clearly, notice that the first two guys are exactly the same. So the standard basis vector will work for the first coordinate because we didn't actually change anything. But this one actually changed a little bit, and that's going to be the guy that changes. So I changed each vector individually, right? So now, this means that to write this vector in terms of B3, all I have to do is multiply it by this matrix. And that will be what it is in the coordinates according to B3. So what would that give us here? It's -1 plus 3. And then 3, right? And notice that you can check what was the standard basis vector again?
2, 4.
It was 2, 4. We should be able to write that as 2, 3 times the basis vector for B3. What was the basis vector for B3? I erased them, so I didn't.
It was 1, -1, and 0, 2.
Right? And that works. So notice I went straight from two very weird bases. I didn't even have to go through the standard bases. I didn't even have to find what it was in terms of the standard R2 bases and then go here. I could go directly from this weird basis to another weird basis. Right? And you can always check that, hey, it actually works out. If I convert both to the standard, I'll see that, hey, the coefficients actually work out. So let me write down a process here. Summary. Let B equals V1, V2, V3, and B prime equals W1, W2, Vn. Wn be bases of n. Then the transition matrix from B to B prime is found by solving this system. V1, put it in the first column. V2, put it in the second column. All the way down to Vn, put it in the last column. And then line up the W1, W2, Wn's here. It will reduce to the identity and P from B to B prime. i.e., put the old basis on the right, the new basis on the left. Here, you put the new basis that you want to change to, and line up the old basis that you want to change from. Find the reduced row echelon form. The matrix that ends up here will be the guy you use to convert from one basis to another. You can find new coordinates of a new basis right away by doing that. And we can compute some vector in terms of basis prime by going from taking the transition from B to B prime of the vector in terms of B. Also, we have a theorem. Any transition matrix P from B to B prime is invertible, and its inverse P from B to B prime inverse actually gives us the transition matrix to go the other way, to go from B prime to B. So we can switch from one basis to another, and we also know how to switch back. Which is a nice thing. So if I have a problem and everything is expressed in terms of one basis, which is a very efficient way to think of a vector space, but the problem happens to be difficult to solve in the basis that I'm in. What I can do is figure out a matrix that transforms it to another basis that might be more convenient, maybe because the basis vectors have a lot of zeros in them or for whatever reason. And then I can solve the problem in that basis, but I'll always be able to change the answer back into the basis that I care about, or that I started with, by just taking the inverse of the matrix that I used to get into the new basis in the first place. And there's a special case where I can state this in terms of the standard. But do I? After this, we're going to do a couple other examples. Well, one more example. Also, we can apply this to the standard basis S. So let's say S is that E1, E2, En for Rn. Then what this means is the transition matrix to go from let V be the, again, V1, V2, Vn be another basis of Rn. Then we can talk about the transition matrices to go from B to S, and the transition matrices to go from S to B. Which one do you think would be easier to compute? There's one thing where we had to find the reducer echelon form that ends up on the left, right? And the guy on the left is supposed to be where our new basis goes. So it turns out if I put the standard basis on the left to begin with, there's literally nothing to do. So this one is actually pretty easy. To go from one basis back to the standard basis, I literally just line up my vectors. And that itself would be a transition matrix. And if I want to go the other way, I simply take the inverse of this matrix. So that's just a special case. But that's because the standard matrix, when you put those all in columns, they already form the identity, so there's almost nothing to do. There's no change that has to be made. Let's do a couple more examples. Example. Let B equals 1, 0, 1, 0, 2, 1, 1, 0, 0. Be a basis for R3. A. Compute PSB. B. Compute PBSC. Let V in terms of the standard basis be 1, 2, 3. Find V in terms of this basis B. P in terms of the basis B is equal to 2, 2, 2, find V in terms of the standard basis. I thought I'd written down answers for these, but I don't think I did. Let's actually do that. B is actually easier, right?
Yeah.
To go from this old basis to the new basis. So the new basis would be 1, 0, 0, 0, 1, 0, 0, 0, 1. This guy would be 1, 0, 1, 0, 2, 1, 1, 0, 0. So that's your transition matrix right away. So P of B to S is that matrix. 1, 0, 1, 0, 2, 0, 1, 1, 0. A. How can I find P of S to B? P of S to B would just be that guy inverse. And that's equal to, what would that be? I didn't write down the answer. Although I feel like we've used this so many times before, so it's probably in your book somewhere. 1, 0, 1, 0, 2, 0, 1, 1, 0. It's probably not that hard to find the inverse. So that's 1, 0, 1, 1, 0, 0. Here I would write 0, 1, 0, 0, 1 half 0, 0, 2 divided by 2. And then I would probably take row 1 minus row 3. This minus, or row 3 minus row 1. This minus this, 0. This minus that, 1. This minus that, minus 1. This minus that, minus 1. This minus that, 0. This minus that, 1. And so now what I can do is, so this is just, this is going way back. 1, 0, 1. 1, 0, 0. This is 0, 1, 0. 0, 1 half. 0, and then I can take something like row 2 minus row 3, 0, 0, 1, 1, a half, minus 1. And then finally I just take row 1 minus row 3, 1, 0, 0, 0, minus a half, 1, 0, 1, 0, 0, a half, 0, 0, 0, 1, 1, a half, minus 1. This means that P of S to B is going to be 0, minus a half, 1, 0, a half, 0, 1, a half, minus 1. Or it's probably nicer to factor out a half. I want to multiply. So that's your answer here. If we didn't make a mistake. 1/2, 0, minus 1, 2, 0, 1, 0, 2, 1, minus 2. So now on to C. So if my V in terms of the standard basis is the vector 1, 2, 3, that means that V in terms of the basis B would be equal to, well, the transition that goes from S to B times Vs. So that would be, transition from S to B is this guy, 1/2, 0, minus 1, 2, 0, 1, 0, 2, 1, minus 2, times 1, 2, 3. So that's 0 minus 2 plus 6. That's 4. And 0 plus 2 plus 0. And 2 plus 2 is 4 minus 6. So that would be the vector 2, 1, minus 1 in terms of the basis. And of course here you can always check. I take 1, 2, 3. Is that actually the same as 2 times 1, 0, 1 plus 1 times 0, 2, 1 minus 1 times 1, 0, 0? Is that true? We made an error somewhere. Should be 2, 1, minus 1. I did write down that answer.
Why is it 1?
Huh?
Why is it 1?
Where?
You get the same solution. You check.
If I get what?
If you check, it's right.
Oh,
Yeah.
oh, it is right, right? Is it?
Yes.
Oh, I didn't. Okay, I thought I must have looked something. That's right. Okay, cool. I don't know what I was looking at, but that should be the answer. Okay, so these guys should be the coefficients of the basis vectors.
Let's check out.
Let's do that last one. There's one example that I really wanted to get to that has polynomials in it. That might be a little bit enlightening, or a little bit, where you can maybe kind of start to see the usefulness of it all. Because changing vectors to other vectors, it might lose impact on you. So I wanted to give you some other scenario to look at. Anyway, so if we have V in terms of B was 2, 2, 2, this means that V in terms of the standard basis would be the transition from B to S of, well, times VB, which would be the transition from B to S, I believe, was 1, 0, 1, 0, 2, 1, 1, 0, 0, 2. And I think the answer here was like 4, 4, 4. Now this example, when we come back to chapter 5, eigenvalues and eigenvectors, you'll see that what just happened was a very special thing that we're going to like to find out. Notice that I just multiplied a vector by a matrix, and what I did was I scaled all the elements by a certain scale. Right? There are times when that happens, and it actually means something nice. But for now, I just want to rush through another example. I didn't realize this would take so long. I got through like a third of what I wanted to get through. Okay. Suppose B equals P1, P2, and B prime equals Q1, Q2 are bases for P1, the set of polynomials that are of 1 degree or less, where P1 is equal to this polynomial, 6 plus 3x. P2 is equal to this polynomial, 10 plus 2x. Q1 is equal to 2, and Q2 is equal to the polynomial 3 plus 2x. A. Find a transition matrix that goes from B prime to B. B. Find the transition matrix that goes from B to B prime. C. Consider the polynomial minus 4 plus x. Find that polynomial in terms of B. D. So one application of this might be familiar to you is back in Calc 3 you might have been asked to find a Taylor polynomial of something centered at a different thing. You could actually think of that as changing a basis, right? Where the polynomial is given to you in terms of x, but you want to write it as a function of x minus 1 or something else. You can actually think of it as doing this process. So you didn't need calculus to do it. You could actually do it using linear algebra. So that's why I thought this example would be nice. Use a transition matrix to find that same polynomial with respect to the other bases. And E, check by computing PB prime directly. Now this is a nice problem. It's a very test-worthy problem, so it is something that if you look in the past finals for 346, you'll see several problems like this. And the functions don't have to be polynomials. We can use trig functions or whatever, and you can actually apply the same idea. And so, first of all, the idea, what we would use is get from we know how to deal with this in terms of matrices. So I would translate from polynomials to vectors in R2. And last time we kind of looked at why we can do this. We'll see more of why we can do this when we talk about isomorphisms. But basically, this was what I was talking about, how we can connect things in an arbitrary vector space to Rn if they're of the same size and they use the same scalars. So that's what I'm actually going to do. So my P1, I'm going to think of it as 2D vectors where I'm going to let the top coordinate represent the constant coefficient and the bottom coordinate represent the coefficient of x. So I'm going to think of P1 as the vector 6, 3. And P2 I can think of as the vector 10, 2. And Q1 I can think of as the vector 2, 0. And Q2 I can think of as the vector 3, 2. Right? And why we can do this you'll fully understand when we actually talk about isomorphisms. Because I can actually create a function from the set of polynomials to the set R2, from the set of first degree polynomials to the set R2, and I can do it in a very convenient way that's 1 to 1 and on to, and everything will be the same. Okay. So now A, what would I call the transition matrix from B to B prime? To do that I would need to solve a certain system, right? I would need to solve. So this is the guy that's the B's, right? And this is the guy that's the B prime. Right? So I want the new basis on this side, 2, 0, 3, 2. The old basis on this side, 6, 3, 10, 2. I find the reducer echelon form. And please tell me I wrote this one down. I did. So it's 1, 0, 0, 1, and this would end up being minus, this is,
I'm doing B.
I'm doing B.
Yeah.
So this one should be B prime to B, right? So this would be, B prime is the old one, so that one goes over here, 2, 0, 3, 2, and 6, 3, 10, 2, and that was 2 over 9, minus 7 over 9, 1 over 3, minus 1 over 6. And so that means your transition matrix from B prime to B is just this matrix here. Minus 2 over 9, 7 over 9, 1 over 3, and minus 1 over 6. And if I went on to B, I can find the transition matrix from B to B prime by simply taking the inverse of this guy. Although it's probably not hard to set up a system like that and solve it again. But that would be, I found that here, I think, yeah, that was this guy. 3 over 4, 7 over 2, 3 over 2, and 1. Now we can go on to C. So here's my polynomial P, which I'm going to think of as minus 4, 1, which means P in terms of B would be this is giving us well, this P is in the standard basis. So all I'm going to do is put these guys here. Take the inverse to get to the standard and put minus 4, 1. This means that P in terms of B would be equal to 2, and I got the answer here. That's 1 minus 1. And also you can do the check here. Check. you can notice that if I look at the polynomial minus 4 plus x, that is actually equal to 1 times the polynomial 6 plus 3x minus 1 times the polynomial 10 plus 2x. That'll actually work out. If I looked at D, and here I want to find P with respect to the basis B prime, I can use the fact that P, B prime will be the transition matrix from B to B prime times P in relation to B, which I just found here. And so the transition matrix B to B prime is this guy, 3 over 4, 7 over 2, 3 over 2, 1, multiplied by my answer here, this, and that would give me the matrix minus 11 over 4, 1 over 2. And you can again check that. You'll notice that if I took minus 4 plus x, it's actually going to be minus 11 over 4 times the other polynomial for b prime. 2 plus a half times the polynomial 3 plus 2x. And finally, B. To compute B with respect to the basis P prime, I would use (2032). This is using the theorem for the standard basis. Invert that and multiply by minus 4, 1. And you'll get the same thing. You'll get this guy. So you can see here, I can express the given polynomial minus 4 plus x as a factoring, a linear combination of several other polynomials. That's useful in a lot of contexts. We'll cover more next time. We'll talk about some really cool applications of that. We'll stop there. We're going to do it quick, but go over this example very slowly. It's going to be a very important example. Problems like this will come up on tests. It's something that's important to know.